So in the last clip, we re-examined what the spectral theorem looks like in the multiplication operator sense, that is the diagonalizability version as it applies to matrices. And now I want to look at the spectral theorem as it applies to matrices for the spectral decomposition form. So going back to what happens when we decompose an operator in terms of projections. So our setup here is, again, suppose we've got an orthonormal basis of eigenvectors for T, and then its matrix is going to be a diagonal matrix. And just like we saw in the last clip, if we apply a polynomial to this diagonal, then since it's a diagonal matrix, and this is an if and only if, it goes straight onto the diagonal, right? So now we can pull this apart as a linear combination. So we've got p lambda 1 times the diagonal matrix 1 with zeros everywhere else, summed up through p lambda n times the square matrix with zeros down the diagonal except for a 1 at the last place. And you can see that this is the matrix of projection onto the first coordinate, right? It just extracts the first coordinate, and this is projection onto the last coordinate. So these are the matrices of the projection operators corresponding to the particular lambda kth eigenspace for each of these. And so we can write this sum as being summed over some index that goes from 1 to n as we run through the list of eigenvalues, or we can just say let's sum it over the list of eigenvalues. Okay, so that's kind of a recap from the last clip. So now let's see. So if we look at a unit vector u, then the projection from V onto the subspace spanned by U is VU U, right? And so if we're in good old Rn with the standard inner product, then this is going to be V dot U times U. And the dot product is actually the same thing as a matrix product if you just write it the right way. So I'm going to put the vector u out in front just for grins, and v dot u I'm going to write as v transpose times u, matrix product. And then that's actually also the same thing as so this one right here, this is a number, this whole thing after we evaluate it, that's a scalar, right? So I can take its transpose and nothing happens. And so this is the same thing as U transpose V. So in other words, this is just the symmetry of the dot product, right? But the reason why I like that is because then I can just drop the parentheses and I see right here an expression for what PU is. So this tells me that the matrix for projection onto U is actually UT. And so this is a construction that comes up in a couple places and is actually useful. So UV transpose is the outer product. And so just like we've got an inner product, turns out that actually is an outer product as well. It's a little less commonly used, but let's kind of break it down here. So if we have oops, I'm using capital T. I think the book uses lowercase t. Let me fix that real quick. Transpose, 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 transpose. Okay. So if we have this widget here, UU transpose V, by associativity we can understand it a couple of ways. So if we do U times U transpose V, then in this case this thing we're looking at here is the inner product of U and V, and you should think of it sort of geometrically as being, well, I don't know if geometrically is the right thing to say, but we always consider these vectors as column vectors. So U transpose is going to be, so here's U transpose, it's a row vector, and then we have our column vector of V that looks like this, right? And so this is going to end up looking like u dot a scalar. And that scalar is the scalar u dot v. Okay, so, and sorry, I don't know if I said dot, but I did not mean that this is a dot product. This is just regular scalar multiple of u by a scalar. And then we can also, by associativity, parenthesize it the other way. So we have u, ut, v, now with the parentheses around here. And in this case, this is the outer product. And so what we get here is we have, let's see, so we've got our column vector u, and then we've got our row vector u transpose times v. And so what happens when you do matrix multiplication like this? Well, you're going to have row 1, column 1, row 1, column 2, row 1, column 3, row 1, column n. And that was all for row 1, but you also have row 2, 3, n. So you're going to end up with a full-on n by n matrix here times v. Okay, but observe that the rank of UU transpose is 1. And so there's two ways to make that observation. One is that you can look straight from the definition and you can see that the range of UUT is the span of U, and so it's clearly one-dimensional, right? And the other thing that you can look at, recalling your 206, is that all rows are scalar multiples of U. So when you do reduced row echelon form and use your row operations to simplify, well, you're only going to get one row left at the end because every other row is a scalar multiple of it, just by the shape of this multiplication right here. Okay, so that leads us to the following interesting application. And so for this application here, we're going to be assuming that lambda 1, or that the eigenvalues are organized in non-increasing order like this. Okay. Then let's see. So if we have an orthonormal basis as our basis here, then we have the projection to one of these eigenvectors looks like, or one of these orthonormal basis vectors rather, looks like this guy. And if we have, say, m strictly less than n, actually here, let me, yeah, there we go. Okay, so I just updated this guy right here, so it's n. But if we take m strictly less than n, then when we look at k equals 1 to m, lambda k, ek, ek, t, this has rank m, because it has rank 1 for each term in the sum. Each term has rank 1. Okay, so then by this ordering right here, so we just cut it off at, say, the mth spot, right here. So then, in fact, this is the best rank m approximation to the original matrix. And so this actually comes up when the matrix that you're interested in doesn't actually come as the matrix of a linear transformation. So suppose A is a matrix of just data. So for example, maybe A is something like, suppose AJK is the distance from point xk to point xj, right? That would be one example. Or suppose that A is some matrix here, which is actually representing the color values of some picture. So here's your friend wearing his hat and glasses, waving. Okay, and so you take this, and this is a digital picture, so it's 100 pixels by 100 pixels, and so we cut this into some grid, and every single one of these pixels is listed as a color value somewhere in your matrix, right? So you just converted that that picture into a matrix. Okay, so then if you want the best rank K approximation to either this matrix here or this matrix here, then you do this eigen decomposition, and you look at EK times EK transpose multiplied by the corresponding eigenvalue, and you sum those up, but you only take the first few, and then you get the best. So if you only take the first M, then you get the best rank M approximation to whatever that is. So that gives you, for example, a lossy compression algorithm for storing your data. Or it also gives you ideas for how to do a data set parameterization. You say, oh, you know what? Suppose I find out that if I only take the first 6 eigenvectors, that gets me a lot of statistical spread. So in other words, the matrix matches up very well with what I had before. Then I might say, you know, that those 6 dimensions, that's really all that defines my data set. I'm going to use that to parameterize everything. So this is the notion of principal components analysis. And we'll revisit this idea a little later on when we look at singular value decomposition. Which is very similar. But I just wanted to give you a preview of coming attractions. So for example, if you've ever done, if you've looked at the Myers-Briggs personality tests, so then you take some quiz for survey form, and you answer a bunch of questions, and then that generates like a 4-letter code for you. So you can, your first one is going to be E or I for introvert or extrovert, and then there's N and T for intuitive or thinking or something like that, and there's J's and F's and P's, and I don't remember what all they are. But what I do know is that these are the first 4 principal eigenvectors. And so what Myers and Briggs did is they figured out, oh, from this survey with like 120 questions and whatever else, basically what works out is that if you just take a 4-dimensional eigenspace, there's the 4th dimension, and this one's like extrovert versus introvert, and then this one's like intuitive versus thinking and whatever else. Wherever you fall with respect to those axes, that determines your personality type.